In today's lesson, we're going to start to look at radicals, and radicals are our square roots that are all listed here. So it's a good idea without a calculator to be able to answer all of your perfect squares from 1 to 121. So keep in mind, a perfect square has an answer of a number multiplied by itself. For example, the square root of 121 is 11, because 11 times 11 equals 121. The square root of 100 is 10. The square root of 81 is 9. Remembering 9 times 9 equals 81. 8. The square root of 49 is 7. So forth and so on, all the way down. So these are all the perfect squares from 1 to 121 that you should be able to answer without using your calculator. Now let's look at this one down here. It's a little bit different. What we see is that 3 is not a perfect square, but the 16 is a perfect square. So the square root of 16 is 4. So I square root the 16, and then I leave the square root of 3 under there. The reason that I don't square root that 3 is that it would give me a decimal. Anytime I square root something to a decimal, then I have to round, and I lose some accuracy. So when I leave my answer like that, I have a perfect solution. Now that we've done a little refresher on square roots, take your time to use your calculator. You can pause the video here and try these questions here that I've listed right here to see that they all give you the same answer. The square root of 24 does equal the square root of 4 times the square root of 6. So if you break apart your factors, 6 times 4 is still 24, it'll give you the same answer. So go ahead and try that. Now that you've checked that yourself, let's look at the proof behind it. Our proof here shows that the square root of a times the square root of b squared, if you separate it, it still works. In the next step, so if you separate it, if I square just the square root of a and just the square root of b, I get a times b, and it works out the same way. So our proof here tests true. Now let's use this to actually start to simplify our radicals. So simplifying radical means that we're going to simplify it the best we can without using our calculator or rounding in any way. So I'm looking for perfect squares that would equal 24. So I know that 4 times 6 equals 24. I can square root the 4, which equals 2. And then I have the square root of 6 left under there. It's like fractions though. You want to be sure that you simplify fully. I checked in my head to see if there was any factors that go into 6 that are perfect squares. And because there's not, then I'm done there. So here, you want to choose the greatest perfect square that goes into 32. 4 times 8 equals 32, but actually using 16, it's a higher perfect square, is more efficient. So I have 16 times 2 equals 32. I can square root the square root the 16, and then I'm left with just the 2 under the radical. Here, we don't need to complicate it. Keep in mind, you don't need to find factors here, because the perfect square of 36, the answer is 6. Here, if I had 25 times 3, I could square root the 25, which equals 5, and then I'm left with just 3 under the radical. Now, you're probably wondering, what does this matter? Why do we need this? If you follow down below here, right here, you realized last year when you started to use the quadratic formula, you often got down to solutions like this: 2 plus the square root of 2 and 2 minus the square root of 2. Last year you would take that and put it in your calculator, and you would have a decimal and you would round. But the more advanced your math gets, we sometimes don't want that rounding because of the loss of accuracy. So you could leave your solution just like that now. All right, let's look at a few more examples here that we can try. So if we want to simplify the square root of 45, 9 times 5 equals 45. The square root of 9 is 3, and I leave that 5 there. Here, I realize that I have like terms. I have 2 square roots of 3 plus 5 square roots of 3. So in order to simplify it, I can add the numbers outside the radicals together and leaving the number under the radical the same. That 3 does not change. Do not add it to form 6. So here we can try to simplify first. I know that 9 times 3 equals 27. And I know that 4 times 3 equals 27. 9 being a perfect square, same with the 4. So the square root of 9 is 3, and left with square root of 3 there. Square root of 4 equals 2. Oh, and I just made a quick mistake there. Have a look. 4 times 2 doesn't equal 12. That should have been 4 times 3. And so now under the radical sign, I'm left with a square root of 3. And because I have like terms, those are the same, I can add them together. 3 plus 2 is 5, and the square root of 3. Take a pause on the video here and see whether you can do this question yourself, and then follow through with the answer afterwards. Alright, so I'm leaving the 4 on the outside. There's nothing I can do to simplify that. I do 4 times 2 under the radical, because that equals 8. I leave that 3, and then I do 9 times 2, because 9 is a perfect square. Now I leave the 4. When I square root this 4, it equals 2. When it comes out, it's going to multiply by that 4 that was already there. This is probably an extra step you don't need as you get good at this. You could have in your head multiplied 4 times 2 right away. So again, I square root the 9, and it equals 3, and then I have the square root of 2 left there. So I'll just finish my last step here. I have 8 times the square root of 2, and 9 times the square root of 2. I have like terms, so I'm left with negative 1 times the square root of 2. Alright, let's finish off this video with the last couple examples, ones that may have some tricks to it that you may not realize right away. So when I see this, I look to try and simplify the square root of 6, and there's no factors that are perfect squares. Same with trying to square root 10, there's no factors that are perfect squares. Because they're both under the radicals, I can multiply them together. 6 times 10 equals 60. And now, even though I couldn't simplify at the beginning, I can now, because I realized that 15 times 4 equals 60. 4 is a perfect square, so I square root that, and I leave the square root of 15 as is. For this question here, there's a couple ways of doing it. I'll show you the first way. The square root of 3 can't be simplified, but we know that 9 times 3 equals 27. That 9 is a perfect square, so I have the square root of 3 times the square root of 3. Outside the radical, we multiply those numbers together. There's just the 3. Under the radical, we can multiply together as well. 3 times 3 equals 9. The square root of 9 is 3, and we see that our final answer there is 9. You might have also started this question by realizing that 3 times 27 equals 81, and the square root of 81 is 9. So a little bit of a faster way to do it. Both ways will get you to the correct answer. I'm going to leave G for you to finish on your own, and we will talk about that in class tomorrow. So be sure that you attempt that one. I'm going to show you a little bit of distributive property with radicals, and that ends the video for today. Alright, so here we just keep in mind that anything that's under the radical can be multiplied by anything under a radical. But for this question here, when I go to the distributive property, the square root of 3 times 2 cannot be done. They're not both under the radical, so it's just left as 2 times the square root of 3. Now when I distribute the square root of 3 times the square root of 6. They're both under the radical, so I can do it. Now, of course, just like fractions, we always look to see if we can reduce or simplify further. I know that 9 times 2 equals 18. I square root that 9, the square root of 2 there. There's nothing else I can do here. This question is finished because I don't have like terms. Don't try to add unlike terms. And this question is left with you with G as well for you to try and bring into class tomorrow.